incidence geometry in connection to theoretical computer science.
So, yes, thank you. Okay, so I'll be talking about incidence geometry and connections. And so the main connection I'm going to be talking about is the connection to the problem of testing polynomial identities. So which is basically, given a polynomial expression, can you decide if it's identically 0? And so here's an example. So suppose you have n variables. St denotes the sum of the tth powers of the variables. Sigma t is the elementary symmetric polynomial in these variables. Then here, this is an expression many of you have probably seen. It's identically 0, and this is the Newton's identity. Okay. So here's another example of another polynomial identity. Suppose you have the Van der Monde matrix. Then here's another expression which everybody must have seen. It's an expression. The determinant is actually a very simple expression in the variables of the determinant. This is another identity which holds. Okay. But what if somebody just comes and gives you an algebraic expression of the following kind? It has many variables, additions, multiplications, and the question is it identically 0? Yes, so the naive way to maybe address this question would be to let's multiply these brackets out, look at all the monomials of the polynomial, see if they all cancel out, and if they do, then it's an identically 0 polynomial, otherwise it's not. But this expansion, multiplying all these brackets out, is very, very inefficient. So the amount of computation time you might take to do such a thing would be exponential in the size of the representation. And so the problem of polynomial identity testing is, can we do this same thing more efficiently? Okay, so the problem more formally is, you're given an arithmetic formula as input. So it has an expression of the kind we just saw. It has maybe n variables. It defines a polynomial of degree d, and the size of the expression is, say, s, and it is made up of some additions and sequence of additions and multiplications. And the question is, you want to decide if this formula is identically 0. And ideally, we want to have an efficient algorithm to do this. So we want to do this in time which is polynomial in the size of the representation. So polynomial in the size of the formula, polynomial in n, d, and s in particular. Okay, so this is a very important problem. And what's remarkable is that though we know very little about actually getting a non-trivial algorithm for deciding what I just said, if you allow randomness as a resource, there's a very, very simple randomized algorithm for deciding if a polynomial is identically 0 or not. So basically, if a polynomial is non-zero, if you evaluate it at a random point from a large enough domain, then its evaluation will be non-zero. And that's an easy way to test if a particular identity holds or not. Just evaluate it at a random point. And if you see 0, then with high probability the expression must actually be identically 0. So there's a very, very simple randomized algorithm, but there's almost no non-trivial deterministic algorithm known for the general question. And de-randomizing this problem would have very, very interesting consequences in complexity theory. This is one of the most natural problems we probably have, which have such a simple randomized solution, but no deterministic algorithm is known. What we do know only holds for special classes of circuits, which are also maybe very interesting. But to understand, we still seem very far from understanding, from de-randomizing the entire class of arithmetic formulae. So what I'll talk about right now is identity testing for a particular class of arithmetic formulae, and we'll see the connection as I describe this problem to the problem of incidence geometry. Okay, so let me talk about what a depth 3 identity is. So I'll be just looking at polynomials of the following kind. So think of k as a constant, maybe 10, and look at polynomials which look like m1 plus m2 up to mk, where each mi is a polynomial which completely factorizes into linear factors. Okay, so the number of variables could be n, the degree could be very high, but I just want the polynomial to be a sum of k many polynomials, each of which completely factorizes, and I'm thinking of k to be a small number here, some constant. So each mi is a product of linear polynomials, these Lij's, where each Lij is the sum of the linear combination of the variables of the polynomial. And you want to ask, suppose someone gives such an expression, is it identically 0 or not? And again, there's no non-trivial, really obvious way of doing it. So just multiplying all the linear forms out and seeing what monomials you get in each mi is, again, the amount of time could be exponential in the length, in the size of the expression. So in joint work with Neeraj Kayal, we showed that, in fact, there is a polynomial time algorithm for deciding identity testing for this class of circuits. And the reason there is such an efficient algorithm is that these polynomials must be actually very, very special polynomials. If you have a sum of these, if you have a sum of polynomials, each of which completely factorizes, and the sum is actually identically 0, then we show that basically this polynomial must be a polynomial only in a very few variables, only in constantly many variables. So what I mean by this is, if you take such an expression, summation mi equal to 0, and you look at all these linear polynomials which appear in this formula. So look at each mi, look at this set of linear polynomials which appear in each of them. And each linear polynomial gives you an n-dimensional vector. You can just look at the coefficient vector of this linear polynomial. Then if you look at the vector space spanned by all these li's, then we show that the dimension of this vector space is actually some constant depending only on k. So it's independent of the number of variables, the degree of the polynomial, etc. So if k is small, then this vector space is just a constant dimensional vector space. And once we can show that, once this expression we can show has only constant dimensional basically, then this is not hard to turn this into a polynomial time algorithm for this question. Okay, so let me describe some of the ideas in how this, the proof of this result, and we'll see the connection.
How big is this f of k as a function of k?
So what we showed was we got something like k to the k, and since then it's been improved to maybe k squared. Yeah.
But somehow, sorry, so you're assuming that the sum is 0.
Yes. So whenever the sum is 0, this dimension must be small. So now given an expression, this is easy to calculate the dimension of the span. If it's going to be larger than this quantity, then you know that there's no way it's going to be 0. And if it's smaller than this quantity, then you can find maybe some invertible linear transformation you can apply to the variables of the polynomial, which will make it a polynomial in only constantly many variables. And once it's a polynomial in constantly many variables, there's a simple brute force algorithm which will decide this question.
I'm sorry, probably I missed something, but if you take m1 and minus m1, and you can take the sum.
It's a very good point. So, so I cheated a bit. So let's assume that the GCD of all these mi's is 1. Okay, so let me quickly give some so this result holds when the GCD is 1, but then the GCD case can be handled separately, and this still gives a polynomial time algorithm for polynomials of this form, even when the GCD is not 1. Okay, so let's just quickly see where incidence geometry comes in. So let's just focus on k equal to 3, which is already a non-trivial case. So suppose you have a polynomial which looks like m1 plus m2 plus m3, which is identically 0. Each mi completely factorizes. Now suppose the variable x1 divides m1 and the variable x2 divides m2. Okay? So let's just set x1 and x2 to 0 in this polynomial expression. So originally we had a polynomial which was 0. If we set x1 and x2 to 0, we still have a polynomial which is identically 0. But when we set x1 and x2 to 0, m1 and m2 completely vanish. So m3 must also vanish because their sum vanishes. So m3 vanished when x1 and x2 got set to 0. So but m3 is a product of linear forms. So if m3 vanishes, some linear factor of m3 in particular must have become identically 0 when we set x1 and x2 to 0, which means that that linear factor must have depended only on the variables x1 and x2. Okay, so some linear combination of x1 and x2 divides m3. And this holds even in general. So if you have any linear form L1 dividing M1 and L2 dividing M2, then some linear combination of L1 and L2 must divide M3. Okay, so if you look at all the linear forms appearing in M1, M2, M3, there are a lot of linear dependencies between them. If you take any linear factor in one of them and a linear factor in another Mi, then some linear combination will divide the third Mi. So there's a lot of structure sitting in these linear forms, and this is what we want to exploit. So let's get a geometric interpretation, and let's get into incidence geometry land from this. So let's get a geometric interpretation of what we've just seen. We'll take all these linear forms which are appearing in the circuit, and we'll map them as points in Rn. Okay, so each linear form which looks like summation ai xi, we'll map it to a point like that. And then it's not hard to see that if 3 linear forms were linearly dependent, then the corresponding points they get mapped to will become collinear. Okay, so we map the linear forms to points, and now let's give these points colors. So all the points which arose from M1, let's color them red. All the points which arose from M2, let's color them blue. And all the points which arose from M3, let's color them green. And what we showed that whenever we took a linear form from M1 and another linear form from M2, the linear combination divided M3. This just means that whenever you take a red point and a blue point and you join the line through them, it passes through a green point. Okay, so now starting with an expression of the kind m1 plus m2 plus m3 which is identically 0, we come up with this configuration of points which has this strange property. So it's a configuration of colored points, and whenever you have a line through two colors, it passes through the third color. And the question we reduced to studying is, suppose we have such a configuration of points, must these points sit in a low dimensional space? If we can show that whenever we have such a configuration of points that sit in a low dimensional space, this would exactly answer the question we were trying to answer about arithmetic circuits. And we show that in fact this is true. So whenever you have a configuration of colored points, and whenever you have a line through two colors, if it passes through the third color, then these points must indeed sit in space maybe of dimension at most 5. And so the core of all our arguments in showing this colored statement is a very famous theorem from incidence geometry called the Sylvester-Gallai Theorem. And so this is a very, very well-known theorem. It's saying a very intuitive sounding fact. And the proof is very neat, and so this is a very, very nice theorem. So the statement is the following, it's very simple. Suppose you have a finite set of points in the plane in R2. And suppose these points are not all collinear, so they span the plane. Okay, then the theorem says there must be a line which passes through exactly 2 points of the set S. So all these lines I've drawn in this figure, they all pass through 3 points. But there is that line which just passes through 2 points. So the theorem says whenever you have a finite set of points, you must be able to find such a line which passes through exactly 2 points.
That's for the real case.
Pardon?
That's for the real case.
For the real case. So right now, everything I'm talking about is in the reals. So everything, let's focus on the field of reals. Okay, and so there's a higher dimension analog of this theorem too, which is less known perhaps, but as interesting, and it's a straightforward generalization of this, which says that if you have a finite set of points which span at least 2t dimensions, then there must be a t-dimensional hyperplane which contains exactly t plus 1 points and is spanned by those t plus 1 points and contains no other point. Okay, so this looks like t plus 1 points in general position. There's a hyperplane through it, and no other point sits on that hyperplane. So these two theorems form the core of our argument, and we show that in fact if you have a finite set of points, each one colored 1 of k colors, and if you have the condition that any hyperplane which passes through k minus 1 colors also passes through the kth color, then these points must sit in a low dimensional space. So this by itself is not fully enough to do the resolve the problem of identity testing for the question we studied, but this is a big part of the argument. So incidence geometry plays a major role in understanding the rank of those identities. And yeah.
So it seems you assume the points are distinct, right?
So exactly. So
every linear form appears in 2 out of the 3.
Exactly. So this theorem would resolve the problem I'm talking about if there's no linear form which gets colored with 2 colors, or equivalently no linear form appears in 2 different of MIs. But what might happen is linear forms might appear in multiple of these MIs, and then it gets much more complicated. So this is not enough. So you need to get a stronger version than this, but it's too complicated to say right now. But this is the simplest case. When when the GCD of any 2 MIs is 1, then this is enough to get the full question. So this gives us a polynomial time algorithm for the case of these arithmetic formulae which had this very special format. It would be very interesting to extend it in various directions, but again very little is known. For instance, we could only handle when the number of these MIs was a constant. But if it's slightly super constant, can you still get a polynomial time algorithm? That would be very interesting. Handle formulae of larger depth, of course general PID formulae. So all these are very interesting questions, and it would be interesting to see if ideas such as these will show up. So this is one problem which I'm very interested in. Let me just not talk about this anymore. Let me talk about another, a couple of slides on another application where these Sylvester-Gallai kind of ideas show up in connections to coding theory. So I'll just define what some open problems in incidence geometry which would have very interesting consequences. So just quickly let me set the notation. So suppose you have a finite set of points in RD. I'll call a line special if it contains at least 3 points from the set. Or I'll call a t-dimensional hyperplane special if it contains at least t plus 2 points from the set. Okay, so very recently there was a very interesting work by Barak-Dvir-Wigderson-Yehudayoff, and they showed the following in some sense, strengthening of the Sylvester-Gallai theorem. They show that suppose you have n points in RD, and it's not, and they don't say that. So Sylvester-Gallai theorem said that every line determined by this point set is special. Then the points must sit in a low-dimensional space. So they said, let's weaken the assumption. Let's say that every point in this point set is contained in many special lines. Then the set of points must be low-dimensional. So more precisely, show that if you have a set of points, so if S is a set of points, and whenever you throw away 1/10 of points, take any subset of size 1/10 of this set and throw it away, then in the remaining set, every point is part of some special line in the remaining set. Suppose you have this condition, then they showed that the dimension of the set of points is some small constant. And so this is an extension of the Sylvester-Gallai theorem, and this shows that two query locally correctable codes don't exist over the real numbers. And this uses some very nice ideas such as matrix scaling. And so one kind of problem which I'm working on is getting a similar result for higher dimensions, which is not known. So can you say the same thing for two-dimensional hyperplanes? Suppose you have a set of points sitting in RD, and whenever you throw away some fraction of the points, then every point outside it is contained in a special two-dimensional hyperplane. Must these points sit in a low-dimensional space? And this is not known, and this would be very, very interesting and have very interesting consequences. So I'll stop here. Thank you.